Have you ever thought about what lies beyond your computer or smartphone? We swipe, scroll, and click without thinking, but beneath every app and every web page is a world of logic and electricity, of tiny decisions made in microseconds. We live in a digital age where information flows faster than ever. Billions of devices around the world are exchanging data right now, powering entertainment, communication, finance, science, and even love. But even with all this power, even with the most advanced supercomputers in the world, we're still limited. Why? Because every one of these machines, from your phone to NASA's servers, speaks the same basic language, binary. Just ones and zeros. This binary logic is incredibly fast and reliable, but it's also rigid. It means computers can only do one thing at a time. They follow rules step by step. If the problem is simple, like calculating your grocery bill, that's perfect. But for complex challenges, simulating nature, cracking encryption, or predicting markets, classical computers slow down a lot. So what if, instead of step-by-step calculation, we had a machine that could explore all possibilities at once? A machine that didn't just follow logic, but danced with probability? Welcome to the world of quantum computing, the next great leap in human technology. In this video, we'll break down what quantum computing is, how it works, where it's being used, and how it could reshape our future. No jargon, no equations, just imagination and curiosity. Let's start at the beginning. The devices you're using, smartphones, laptops, smart TVs, they all run on classical computers. And at their core, they use bits, tiny on-off switches, representing ones and zeros. Millions, even billions, of these bits work together to store files, browse the web, or simulate entire worlds in games. This system has taken us far. From the moon landing to self-driving cars. But it's not enough for the next frontier. Think about problems like discovering new drugs, breaking encryption, understanding black holes, creating materials at the atomic level, designing global traffic systems in real time. These require more than brute force. They require parallel thinking. And that's where quantum computing enters. So, what exactly is quantum computing? At its core, it's not just a faster computer. It's a completely different kind of computer, one that leverages the bizarre rules of quantum mechanics. Instead of bits, quantum computers use qubits. A qubit can be both 1 and 0 at the same time, thanks to a property called superposition. Imagine a coin spinning in the air. Is it heads or tails? While it's spinning, it's both. That's your qubit. Now, imagine two coins spinning. Not only can they be in multiple states at once, but they can also be entangled, a quantum phenomenon where changing one instantly changes the other, even if they're miles apart. Einstein once called this spooky action at a distance. But spooky or not, this is the fuel of quantum computation. Superposition and entanglement allow quantum computers to do what classical machines can't, explore all possible solutions in parallel. Here's an example. Imagine you're lost in a giant maze with a million paths. A classical computer will try one path at a time, fast, but still sequential. A quantum computer? It tries all the paths simultaneously, instantly narrowing down the best route. It's like comparing a flashlight to the sun. Both shine light, but the scale is completely different. But quantum computing is not just theory anymore. It's real. It's happening now. Governments, corporations, and research labs are racing to build the most powerful quantum machines. Google, IBM, Microsoft, Intel, Amazon, and startups like Rigidity, IonQ, and D-Wave are pioneering hardware, software, and use cases. In 2019, Google claimed it achieved quantum supremacy, solving a problem that would take a supercomputer 10,000 years in just 200 seconds. While the claim sparked debate, one thing was clear: we're entering a new era. But how do we build such machines? Qubits are fragile. They must be isolated from heat, light, and even air. Most quantum systems operate at temperatures near absolute zero, colder than space itself. The engineering challenges are massive. Some machines use superconducting circuits cooled with liquid helium. Others use trapped ions held in place by lasers. Newer experiments use photons, particles of light, to create optical qubits. Maintaining quantum coherence, keeping qubits stable, is like trying to balance a pencil on its tip during an earthquake. That's why we're still in the NISQ era, noisy intermediate-scale quantum. These machines exist, but they're error-prone, small-scale, and still experimental. But make no mistake, we've crossed the threshold. And now the race is on. So what can quantum computers actually do? Let's explore some powerful real-world applications, not just dreams, but work already in progress. DNA 1. Drug discovery. Imagine simulating the behavior of a molecule, not with guesses or approximations, but atom by atom, quantum state by quantum state. Quantum computers could unlock cures for diseases faster than ever before, designing new medications in days instead of years. Closed lock 2. Cybersecurity. Most of today's encryption relies on the difficulty of factoring massive numbers, something classical computers struggle with. But a quantum computer running an algorithm like Shaw's could break these codes in minutes. Scary? Yes. But the same technology could also create quantum encryption, communications so secure, they're physically impossible to intercept. Flying money. 3. Finance. From optimizing massive investment portfolios to spotting fraud hidden in mountains of data, quantum computing could revolutionize global finance, running simulations and predictions that would take current systems years. Globe. 4. Climate modeling. The Earth's climate is one of the most complex systems we know. Quantum simulations could help predict extreme weather events, test climate solutions, and even model carbon capture technologies in ways classical supercomputers simply can't. Battery. 5. Energy. Quantum models can help design better solar cells, longer-lasting batteries, and more efficient power grids. Think of a battery that lasts twice as long, not because of guesswork, but because we simulated its chemistry at the quantum level. Robot. 6. Artificial intelligence. Machine learning, one of today's hottest technologies, is also a good fit for quantum speedups. Quantum algorithms could enhance pattern recognition, make neural networks faster, and allow AI to learn in ways that mimic the brain more closely than ever before. But here's the thing, none of this means you'll have a quantum laptop tomorrow. These are not devices we'll use directly, they all live in the cloud, in labs, in data centers, quietly reshaping the world behind the scenes. So what's holding us back? Red exclamation mark. The quantum challenges. We're still early in the quantum journey, and there are real roadblocks: qubit stability, coherence time. A qubit has to stay in its quantum state long enough to perform a calculation. Right now, that's measured in milliseconds. Error rates. Quantum systems are fragile, and small vibrations, heat, or magnetic fields can mess things up. Quantum error correction is still developing. Scaling. Going from 50 to 1000 qubits sounds small, but it's a massive leap in engineering. Software. We need quantum programming languages, compilers, and entire new ways of thinking about code. This is not just classical programming 2.0. Yet, progress is happening faster than expected. Globe. The global quantum race. Countries are pouring billions into quantum research, not just for science, but for power, influence, and security. The US has multiple government initiatives and private giants like IBM and Google leading the charge. China is investing heavily in quantum communication and even launched the first quantum satellite. Germany, Canada, India, the UK, Japan, all are racing to secure a place in this future. Universities are launching entire quantum computing programs. Startups are booming. Even high school students are now learning quantum basics through online courses and simulators. Rocket. What comes next? Over the next 5 to 10 years, here's what we might see: quantum cloud access, like AWS or Google Cloud, but for quantum enhanced AI models, smart assistants that understand more nuance and complexity. Quantum sensors, ultra-precise navigation tools, medical devices, and telescopes. New careers, from quantum algorithm designers to error correction engineers, new job fields will open. This isn't just a tech trend, it's a full-blown scientific revolution. Light bulb. Final thoughts. Quantum computing challenges our assumptions, about computation, about nature, even about reality. It asks us to think differently. What if something can be true and false, at the same time? What if two things can be connected, even if they're far apart? What if answers exist in a cloud of probabilities, not a list of options? It's not just a new kind of machine, it's a new way of thinking. So the next time you scroll through your phone or ask your smart speaker a question, remember, you're seeing the world through classical eyes. But just beyond the screen, a new world is forming. One that's stranger, deeper, and more powerful than anything we've known before. The quantum revolution has already begun.